We will get started here. Hello, everyone. Thank you so much for joining us today. My name is Christina Wolford, the Director of Education with the International Biometrics Society. I'd like to welcome you today. Thank you so much. Before we start, I want to go over a few housekeeping items. And we have a couple here. We just want you to keep your questions and comments simple, keep it short, speak slowly and clearly, and build the discussion in a positive way, be constructive, respect others, use the raise your hand function if you would like to speak or ask a question. We also ask that you mute your microphone unless you are speaking. The paper and other supporting documents are available in your registration email, and this recorded session will be made available afterwards. So if you do not mute your microphone, all those comments and background noise will be recorded. So try to keep that in mind. So I would like to now hand this over to Dr. Jim Todd. He is our Journal Club organizer and chair. Jim, go ahead.
Lovely. Thank you very much, Kirsty, and thank you for all of you for attending the Journal Club. We hope this is informative and useful. We like to have this opportunity to network and interact and discuss new statistical issues. We're pleased to have Silvia Montagna here with us to present the paper, and Mark Fiecas, who will be leading the discussion on the paper. So after the discussion, I'd like everyone to feel free to engage with the discussions and ask questions, but let's think about how we can use the ideas from this paper. So with no further ado, I will hand over the floor to Silvia and to present the paper on spatial Bayesian latent factor regression modeling of CBMA data. Thank you. Sylvia, it's all yours.
Well, thank you very much. So thanks for having me here today. So before I begin, I would like to acknowledge my co-authors for this paper, Tor and Lisa, who provided the data, and Tim Johnson and Thomas Nicols, who supervised the methodological development. This work was primarily developed at Warwick while I was working on my postdoc. So this is a brief outline of the talk, so introduction and background, primarily on the application. Then we will jump into the model. We will talk about reverse inference and how we can do it, and a few conclusions. So the topic here is meta-analysis of functional MRI studies. So in the past 2 decades or so, fMRI has become an essential tool for learning patterns of activation of the human brain. And there are lots of neuroimaging experiments trying to study and investigate different paradigms, see which parts of the brain become active when a person is engaged in a certain task. The problem is that single fMRI experiments suffer from some limitations. The primary problem is related to the cost of using an MRI scanner. It's quite expensive, as you can imagine. So typically, this affects the number of people that you are able to scan in a single experiment, which often doesn't go above 20. And we will see some summary statistics, in fact, about the data that I used for this paper. So if you cannot scan a lot of people, then you incur into other problems, primarily the analysis suffer from low power and also poor reproducibility. It's not unusual to scan the same people. You want to investigate the same tasks or the same cognitive process. You just do it in 2 different sessions under the same experimental conditions, and you might get different results. So to overcome limitations that affect single fMRI experiments, there has been an increased interest in meta-analysis. So we try to combine similar but independent studies to investigate the degree of agreement and try to find consistent results. So the goals of a meta-analysis are twofold. I would say the main one is so-called forward inference. So we want to combine different studies that investigate similar processes and find consistent areas of activations in the brain. And we want to discount chance findings. So this is called forward inference. And in probability terms, we will frame it as we try to estimate the probability of activation given a certain task. So we know that the neuroimaging experiment looked at a particular task. But neuroscientists are also very interested in the so-called reverse inference. So given a certain activation pattern, I want to infer which one is the most likely, let's say, cognitive process that gave rise to that particular activation pattern I observed. So for a statistician point of view, this is a classification problem. I observe an activation and I want to know what was the task, or let's say the class, right, that gave rise to that particular activation. So in probability terms, this is the probability of a given task given an observed activation pattern. Now, the second one is much, as you can imagine, is much harder to accomplish than the first one. And there is a lot of mispractice in here as well, because it's difficult primarily because it's known that a given brain region may become activated by several different tasks. So do reverse inference is much harder than forward inference. Now, the type of data that I'm looking at is a little bit particular because when I talk about fMRI experiments, people usually think that I'm working with images, right, fMRI scans. But in reality, when neuroscientists collect their data, they do some pre-processing, and then they run some preliminary statistical analysis using available software. These are very simple analyses that they run, let's say, fixed or random effects, linear model at each voxel in the brain independently. They obtain images of parameter estimates and test statistics, and then they threshold these images for significance. And when they publish their results, they only report the XYZ location of peak activations, so the so-called foci. So if they find that in the brain there is one voxel that is active, they just report the XYZ coordinate of that voxel. So this is what my data set looks like. You can imagine that, let's say, the data on the left over here are, let's say, the coordinates of a particular neuroimaging experiment that was, let's say, investigating pain. And so this is what the data set looks like. And if you pull them out, if you pull the different neuroimaging experiments all together, the data look like the image to the right. So you have points in a given brain template. Okay, so we are not looking at fMRI scans, but this is what the data looks like. We have points in a given brain template. So we need to build a suitable model for this type of data. And the goal here, or what we try to do in the paper, is to propose a Bayesian hierarchical model that can both accommodate forward and reverse inference for coordinate-based meta-analysis data. Okay? So because of the nature of the data, we went borrowing from the spatial statistics literature, really. So in terms of notation, we have capital N independent observations, which are our N studies that get into my meta-analysis. So we have capital N independent point patterns. And we call the foci, so the set of points that get reported by the different studies, as lowercase xi. Okay, so each study reports a set of foci, peak activation coordinates. And generally, the number of foci reported by each study, this ni, is very small, about 4 or 5. This is the mean. Now, we think of lowercase xi, so my point patterns, as a realization from a Cox process, capital Xi, which is driven by a random intensity function, mu I. So here you see the sampling distribution. We are assuming that our point patterns are independent. And so the sampling distribution is let's say, proportional to the product of the individual contributing distribution. So mu I is the study-specific random intensity function, which in our case is a non-negative 3D surface, which we need to estimate, and mi is the non-negative random measure, right? And B is the common brain template. So for this is basically our likelihood, what the shape of the likelihood we need to work with. And here the inference is based on the intensity. So we need to propose a model for the intensity and estimate it. So here we need to decide how we model mu I and infer mu I, which is this 3D surface which models my and shows my activation patterns. So there are several possible ways, obviously, but what we looked at in the paper was to write log mu I, this has to be non-negative, through a functional representation. So we expand log mu I, or we think of log mu I as lying in the linear span of some fixed bases that I call here B. These are fixed basis functions. They can be splines, 3D Gaussian kernels, or really anything you want, depending on the application. And we have P of them, so we throw in P basis functions that you choose a priori, times some basis function coefficients that I'm calling theta I. They're also called scores. Now, because the basis functions are fixed a priori and they're common across the different studies, now all the variations in the study-specific intensities mu i's are reflected in variations through the score vectors. Now, the idea here is that we choose the bases, we throw into our model a large number of bases, so P is typically large, especially in a 3D application, and then what we are going to try to do is to discard the bases that we do not need to represent our activation patterns. Now, to achieve this goal, we place a factor model on the basis function coefficients. So we model theta I in the typical latent factor representation. So we have lambda, which is our factor loading matrix, a tall and thin matrix that tends to be or should be sparse. And the number of columns of this matrix K is much smaller than the number of basis functions we have into our model, we put into our model. And this is very important for something we see later. Eta I is the vector of latent factors. Again, this is a study-specific vector of latent factors. And then we have the usual residual vector uncorrelated with other variables. Now, because we are embedding all this in a Bayesian framework, we need to assign prior distributions to all these parameters. Now, typically, the latent factors, the eta I, are given a standard normal prior distribution. However, if you do have covariate information, in our case on the individual studies, we can incorporate covariate informations, here the covariates are ZI, through a simple linear model on the latent factors. So covariate information here could be the year of the publication of this particular experiment, or let's say whether the study, well, the number of subject scans, for example, or whether the preliminary analysis that the neuroscientists runs were fixed or random effect models. We'll see some examples of covariates later on. So if we have covariate information, we can include them into the model, and then they impact them on the foci in a sort of indirect way because they affect the latent factors. Now, these representations, so far we are building a hierarchical model, right? So we have our sampling distribution, then we have the representation for the intensity and the latent factor model on the basis function coefficient. Now, this structure induces a low-dimensional representation of the log mu I, which we really want because of the dimensionality of the problem. And you see it here. Now, if you simply rearrange the terms that we have right now in our model, you see that there is an equivalent representation for the log mu I. So the eta, which are our latent factors, can be interpreted themselves as coefficients for some basis functions. But the basis functions are these tildes here, which are a linear combination of the fixed basis functions we choose and the factor loadings. And these form a new non-local basis set that has to be learned from the data. And again, this basis expansion is we are representing log mu I as a random intercept Ri plus an expansion of k basis functions where k is much smaller than p, and these bases will have a nice structure. This decomposition in some sense reminds me of functional principal component analysis because these learned bases will have some structure in them that remind us of the eigenvectors, even though they're not quite the same thing. And the key here is to have these representation and look into these phi's to see how they differ from the fixed bases that we choose a priori. So in terms of implementation, I don't want to say too much about it, but everything is, the model is embedded into a Bayesian framework, so we will choose whenever possible conditionally conjugate prior distributions for the model parameters. But the most important prior that we have here is the prior we choose on the factor loading, so the lambda matrix. And the prior we choose is the multiplicative gamma process shrinkage prior. So this prior shrinks the factor loadings increasingly as the column index increases. So in this tall and thin matrix that we have here, we have a prior that shrinks the elements of this matrix increasingly as the column index increases. Now, the intuitive idea here is that the first few latent factors are important in explaining the activation patterns we observe, and the subsequent ones are less important. And so in some sense, they are redundant. There is also another component of these priors that make sure that we are not over-shrinking the elements within each column. Now, this prior is very important because it induces some nice feature. Let's say it puts a nice representation to these phi tildes, and we will see it later. So they have decreasing magnitude, essentially. So let's see how this performs on our application. So the application that we used in the paper was a meta-analysis data set of emotions. So we collected 62 publications on 5 emotions that you see here. And these are all the foci for different emotions. So you don't really see too much into these pictures. In fact, the 5 emotions tend to have, let's say, overlapping activations, right? They tend to, let's say, cluster in the same points in the brain. Now, these are a few data summaries. So you have the number of studies per publication, because each publication may report several single fMRI or experiments. So you have a minimum of 1 study per publication to a maximum of 9. And then you have 2 interesting things here: the number of foci per study, so how many peak activation, let's say, a single fMRI experiment it finds, and you see these aren't very many. The median and the mean number of foci reported by a single neuroimaging experiments is 4 and 5 respectively, so these are really sparse data sets themselves. So we have to estimate these mu i's, which are study-specific intensity functions, but each study just gives me, on average, 5 foci. So here, borrowing of information becomes crucial across studies. And the number of subjects per study, so how many people were scanned by that particular experiment, you see you don't really go often beyond or above 13, on the mean is 13. So really you scan quite a small number of people. And then you have the total number of foci and the number of studies per emotion. On this particular data set, we also have some covariates. We observed the modality. It's not uncommon to put together PET and fMRI studies. So there are two different modalities, but they are often combined in meta-analysis. Now, the inference method, so what type of statistical analysis the neuroscientists run to identify the foci, so either a fixed or random effects model, the number of subjects scanned, the type of stimulus, and then this is important, whether the p-values were corrected or not, because again, the neuroscientists run independent analysis at each voxel and then determines whether each voxel is active or not. So you have thousands of p-values and ideally you would correct, but sometimes they're not corrected for multiplicity. So we see what happens here. So the maps that you see here are mean posterior log intensity. So this is for all the studies that fall in a particular emotion type, you have the average of the log intensities. So you see across the emotions, now the degree varies across emotions, but you tend to see these, let's see if I can use this, okay, these white blobs over here. These are the amygdales, which are almond-shaped regions that are known to be involved in emotion processing. So to some degrees, all the different emotions pick up the amygdala. And these are only 3 axial slices of a full 3D analysis. What I also find interesting is this plot. These are the learned bases. So those bases, those tildes or phi tildes that I have in my decomposition of log mu-i's. And then these again are unknown non-local bases that are learned from the data. And what I see here and what I like is that I start my model, let's say, throwing in Gaussian kernels or B-splines, but then what the method actually learns are these bases. And these are the bases that I need to represent my activation patterns. So remember, these are a linear combination of my fixed bases and my factor loadings. Now, if you see, so for example, you see that the first basis in this decomposition really captures the amygdala, for example, and then the following ones, these are index increasing, they seem to pick up some other blobs here and there that might be activation or deactivation. Now, the magnitude of these bases, if you can see, decreases as the index of the basis increases. And this is not happening by chance, but is an effect due to the multiplicative gamma process shrinkage prior, because as I said, I shrink increasingly as the column index increases. So this has the effect of decreasing the magnitude of these bases, which is nice as from an interpretation point of view, because the first basis captures let's say, the most important patterns of activation, as you would say, the first eigenfunction, and then the subsequent one tends to, let's say, explain the residual variations in the data. Now, you shouldn't read too much into these bases. These are not eigenfunctions, they're not orthogonal, but I like the idea of being able to visualize what the model picks up in terms of learned basis. Now, we might also want to see what the impact of the covariates is. In fact, one of the referees asked this. So our model really simply is a finite rank Gaussian process for the log intensities, which has a covariate dependent mean function. So remember here, the z's are the covariates. So you have covariate j on study high times some maps, the learned bases again, and some covariate coefficients. This is the covariate coefficient matrix that we had on the model 48i, and the common covariance functions. Now, what I care, if I want to assess the impact of the covariates, is to look at these maps, because these maps show me the expected difference in a mean log intensity function at a particular voxel, given a 1 unit change in the value of covariate j. all other things being equal. So it's a sort of usual interpretation of, let's say, a covariate coefficient, even though here we're looking at maps. So we can see what these maps look like. And this is what the next plot is. So here I'm only showing you 3 maps for 3 covariates because the other ones don't really show any patterns. So the first one is this particular quantity. Again, this particular quantity here plot for the covariate modality. So I'm going to pick all the coefficients, it's a vector, that refer to the modality covariate. So what you see here, okay, oops, too much. So what you see here, again, you have this map. This is, again, a 3-dimensional map. I'm showing you 6 axial slices, and you see the effect of modality. So what happens if you go from a PET study to an fMRI? So all these maps are on the same scale, and in particular, lighter image shows a higher log intensity, or a higher mean estimated log intensity. So it seems that if you move from a PET study to an fMRI study, you are more likely to observe more foci in the amygdala. And the same, and I think there was an explanation for this. I think the fMRI studies have higher resolutions than PET, or Mark might say something about this. You don't observe really much an effect for the inference method, but thankfully, much to my relief, you can see what you would expect for the effect of p-values. So if you go from studies that correct for multiplicity to a study that doesn't correct for multiplicity, you tend to observe more foci. So your log intensity function is going to be higher, in particular is going to be higher at the amygdala, and then therefore you're more likely to observe more foci, which is expected. So you should correct. These could be false positives. Now, so far we haven't really said anything about reverse inference. Everything we have said so far was for the forward inference. We have built a model for the activation patterns, or let's say our foci. But then again, the neuroscientist really is interested in reverse inference. So the neuroscientist might say, well, if you observe this particular, let's say this one, this particular activation, can you tell me what was the emotion that gave rise to this activation pattern? So can you predict it was disgust versus anger, fear, happy, or sad? So for us, it's a classification problem, right? Now, the idea here is that we can build a model for the study type. So in our case, the study type is an unordered categorical variable. So we build a model for the study type, really whichever you want. You can use a multinomial logit or a multinomial probit, or in fact the ones we use in the paper, which is called diagonal orthant multinomial probit. Or you use a different type of model if you have a different type of outcome. But then the key idea here is to use the latent factors, the eta I, to link the 2 component models. So the model that you build for the foci and the model you build for the study type. And I think this is better represented through an image. So at the center here you have the latent factors, which are the key component in our construction, potentially covariates impacting on the latent factors. So what we see on the right is the model that we have built for the foci, or for the log intensities. And then here on the left is the study type model. So let's say if our outcome is an order categorical as the emotion type, we will have a probability that study I is of type J, and I build a model for this probability where in this, I define this probability, and in defining this probability, I use the latent factors for study I. So I will have some study-specific parameters, emotion-specific parameters, alpha and J, and then the latent factors. So the latent factors become the key component models, the key component that links the two component models. So this is a sort of scalar or vector on function regression, but instead of doing it in the traditional way where we define a model for the outcome and then we see how we can represent our covariates, which in our case are the activation patterns, we build two building blocks and then we join them through the latent factors. Okay? So performance, well, for this particular data set, I held out and predicted 20% of the emotion types. So I created a test set and I held out the emotion type for this test set. And this is the classification performance of our method compared to some state-of-the-art methodology, multi-level kernel density analysis combined with a naive Bayes classifier. I would like to show you that classification is better than what it is. Classification is not optimal. The average correct classification rate for the model is 0.26 as opposed to a 0.25. So it's not ideal. You would like to be doing better, but at the same time, it's quite difficult. It's a difficult data set. Emotions tend to really, the different types of emotion really tend to engage primarily the amygdala. And with the current resolution of the scanner, which was 2 by 2 by 2 millimeters, it's really difficult. You don't have a really fine grid there, so it's really difficult, I would say, to make a prediction or classification among the different emotions. But at least we are above random chance and improving a little bit over, let's say, state-of-the-art methodologies. So to summarize, we have proposed a unified approach for reverse inference of CBNA data, taking into account the spatial structure of the data. We can accommodate meta regression, but I think what I like the most about the method is that besides the application, the method is really it is flexible and you could, let's say, use it in a variety of applications. So if you don't have point pattern data, you might have, let's say, functions or you're modeling hormone trajectories. You can change the likelihood, but you still retain the lower levels of the hierarchy, and you can still keep the model. And if your outcome is not an order categorical, but it's binary or it's continuous, you can change this component of the model and then retain the main idea of linking them through the latent factors. So I like essentially the flexibility that can extend beyond this particular application. Okay, so that's it.
Yeah.
And some references that I cited throughout the presentation.
Thank you very much, Silvia. That's a very interesting talk, and thank you for explaining your paper so well. Right, I think we should ask Mark if he wants to give us a short discussant on the paper. Mark, you ready?
Yep, I'm ready. Can you hear me okay?
Yep.
Yeah.
Okay. So before I start the discussion, I want to just put a little preface out there that so I was at the University of Warwick with Silvia when she was developing this. I'm now at University of Minnesota, and so I just want to put that Silvia and I are not exactly completely independent. Silvia touched on a number of issues in neuroimaging studies, and for this discussion, I want to split this into two things. One, elaborate further on the challenges in fMRI. And then number two, I'd like to broaden this more to the challenges in point process models. So for the first part, regarding challenges in fMRI, the data, let's back up to a single study. So in a single study, what you have here, you decompose the brain into essentially 300,000 spatial locations. And for each point in space, you test, you do some sort of statistical inference. Is this spatial location in the brain active or not? So Silvia touched on this regarding the multiple comparisons or the multiplicity problem. We're talking about a very severe multiple comparison problem where all your tests are also highly correlated because they are correlated over space. Furthermore, your data are time series, right? They're fMRI, so they're also correlated over time. So you have this very complex spatial temporal structure in the original data, and that's just for a single subject. Okay. So there's been a lot of, people have really looked into this problem regarding just multiple comparisons for fMRI. And a lot of, there's a lot of very popular softwares out there on how to do the analysis and what we can do for multiple comparisons. And some of it actually boils down to a bunch of simple point and clicks, which is fine. However, one thing that I want to point out is the following. Sometimes, that this problem is actually much harder than what we think. So this is this paper here. This is a PNAS paper published about 3 or 4 years ago by Anders Eklund. Tom Nicols, the second author here, he's actually also a co-author of the paper that Silvia talked about. So I just extracted the significance paragraph in that PNAS paper, and I want to point out the highlighted phrase there. Again, so even after you account for all the challenges in fMRI, just a very naive way to do hypothesis testing. So one of the ways they do it is what's called cluster-based inference, which is I'm not going to declare a spatial point in the brain to be active unless its neighbors are also active. So that's what essentially was this cluster-based inference. But even still, based on this highlighted phrase, even still, we can actually get false positive rates that are just very, very high, much more than what we think. Right? Usually we go for this nominal rate of 5%, but even after for accounting for the spatial structure, it's very challenging. And I'm going to tie this to why we should care about this, but just have this in mind. So this is for a single study. I'm not even talking about meta-analysis yet. So for a single study, just any degree of multiple comparisons is very hard to do. What I'm not showing this paper, by the way, this paper is very good to read and very accessible to those if you have never seen an fMRI study. It's definitely worth reading just to see the challenges. And one thing I'm not showing here is one approach that they advocate for, something that does a much better job of preserving that nominal 5% type 1 error rate, is to do permutation-based tests. So for those who have done permutation tests before, you can also know that, well, that's just going to make your computational complexity even more. So if you're already having problems with just fitting models and you've got to do permutation tests on top of that, and you can see how this can become a very computationally burdensome analysis to conduct. So this is at the inference level. Now let me take another step back. Let's talk about the modeling level. Okay. This is a paper by John Aston, who was at Cambridge and also previously before Warwick. He now is a scientific advisor to the Home Office in the UK. So this paper is still under review, but you can see a version of it on arXiv. I have the link there. So I'm only just presenting one challenge at the modeling part, which is how to account for the fact that you have temporal autocorrelation in your data. What this paper talks about is actually they compare how the existing software, how accurate they are when it comes to modeling the degree of the temporal autocorrelation, and how that then affects subsequent inference. So this is all, so this is taking another step back. And what they showed here is, again, how you do it can affect your inference. So we have to think about not only how we do our multiple comparisons, but even before that, how do we do our model? And all these choices that we make. And to make this problem a little bit worse, even before you get the data, so Silvia touched on this a little bit, there's a thing called pre-processing, and it turns out that how you pre-process your data also matters. Okay? So what pre-processing is that no one analyzes the images right as they come out of the scanner. So you can think of this as a type of data smoothing of sorts, that we want to account for certain artifacts that occur during the study. For instance, in an fMRI experiment, you stick a person in the scanner for anywhere as short as 5 minutes to as long as an hour, and you ask them to stay there and not move for more than 2 millimeters. That's going to be very, very hard. So that's the problem with respect to motion. There's also the problem with respect to the fact that the size and shape of your brain is different from the size and shape of my brain, and so on and so forth. So how then do you pool images across people? So that's what's actually called normalization. So these types of things are these steps before you even do the analysis. Those are called the pre-processing steps. And there's a number of studies out there. I'm showing 3 papers here that show that, well, how you do it, how you pre-process your data can actually affect your results. And in some cases, there's actually a quote-unquote optimal way to pre-process your data. And in fact, what some of these papers are showing is that how you pre-process one subject need not necessarily be the same as how you pre-process the next subject. So you can see how this then becomes extremely complicated. That even before we even do any analysis, how we even get our data, and there's already things that we have to think about. When it comes out of the scanner, we have to think about pre-processing already. And then once we have the pre-processed data, once we have some way of smoothing the data out so that it's ready for analysis, then we have to make choices about how we model, say, temporal and spatial correlation. And once we have that, then we have to start thinking about inference. Now, the reason why I bring all that up is because when it comes to meta-analysis, so you're kind of conditioning on all those steps already. So the data, say those the foci that Silvia had, that's already after all these steps that they've already, that these experimenters have already taken. So in some sense, what I'm trying to say here is that there might be more variability than you expect. Now, what Silvia has done, is pretty good, and in fact, there is one way to try to account for some of these things, namely, trying to incorporate those covariates, and it's one step, towards addressing the large degree of heterogeneity across studies. But you can see how that there's still a lot of room for us to make improvements on how we can proceed on accounting for this source of variability. So that's all in the neuroimaging side. Now I'd like to take this, spin this back to spatial point processes again. So very simply, when we're talking about 300 spatial locations in the brain, that's a really hard problem. Okay? So this is if you just even imagine that spatial correlation matrix that you have to deal with, 300,000 spatial locations. That's extremely challenging, and there's been a lot of recent work now, on trying to deal with this. This first paper here from the Lancet. So this is actually a meta-analysis looking at the prevalence of a very specific disease. So this is now detached from neuroimaging. It's still a meta-analysis of point processes. So in fact, some of the things that Silvia has developed, some actually can be applied it's not just their specific to fMRI studies. You can take it into other directions, such as spatial epidemiology. So in this Lancet paper, yeah, they're talking about the prevalence of a disease. They looked at a bunch of papers that studied that, and now let's do a meta-analysis and and try to get that the spatial try to account for the spatial structure in the data. So something that they kind of just brought up in one sentence is actually how they did that, and that's this JRSS-B paper below on how to model random fields in this case, and so when you have very complicated, let's just put it that when you have complex data, sometimes you need complex models, and sometimes there just is no way around that. And so this paper by Howard Drew looks it's a type of INLA approach, so integrated nested Laplace approximations on Gaussian random fields, and it's something that the mathematics and the statistical methodologies there are pretty complex, but sometimes that's what's necessary. I do recommend, if you're interested in, say, look on how to do INLA for these for spatial random fields, have a look at this paper, especially since they also have an R package that you can use. So this is just one out of many. Okay. So I'm just bringing up here a couple of other papers. This top one again is with respect to using INLA for special point processes. Silvia's paper is actually an extension of this paper by Jian Kang. In fact, she was citing his paper a couple of times, and you might notice some of the same co-authors here. So this second paper is in JASA, so if you are interested in, say, making comparisons between different point process models, have a look at the literature review on the challenges of point processes, and, for example, how Silvia addressed some of the challenges that Jian Kang encountered. As for those of you who are very familiar with the literature, Peter Diggle is a very famous name in spatial statistics. He's also been working a lot with LGCPs, log Gaussian Cox processes, again, the models, so Silvia's application is fMRI, but Peter Diggle, this one is now in geostatistics. So anytime you have, spatial point process patterns, it need not be, right, with respect to fMRI. Spatial epidemiology has a lot of it. Ecology has a lot of it going on. So the applications are definitely very broad, and everything that Silvia has talked about was from a modeling perspective. Some of those ideas also transfer over into other applications. However, just as how I talked about the challenges in a single fMRI study, when it comes to meta-analyses, to also think about, say, the challenges in a single geostatistical study or challenges in a spatial epidemiology study, to kind of have a feel for the sources of variability and what comes into play when you have those spatial coordinates. So I'll end my discussion section there. So.
Thank you very much, Mark. Thank you. Yep. Thank you, Mark. So that sort of presented a lot of the challenges, and I think made us realize how difficult this is, but it will improve as the data quality improves, I think.
At this time, we do not have any questions in the queue. If people do have questions, you can use the chat feature on the left-hand side of the page, the bottom left-hand, and submit your questions there.
Actually make a comment about something that Mark said. I guess I can go. So I think it was really great in explaining the pre-processing steps. And as I said, yes, there is a lot that goes on before you can even do any statistical analysis. And obviously this is not something we, say, statisticians have that much control of, especially if we want to do meta-analysis, unless we are there to assist the neuroscientists and potentially provide ideas. In terms of the data, I have to, one one of the problems, I would say, as it said, there's no common standards for even running these analyses. It is true that nowadays, I think, there is, or hopefully there will be in the future, the tendency to start sharing the images of parameters or test statistics. So instead of, there are people trying to really create repositories so that neuroscientists can then publish their images. So again, to give you an idea, you fit a linear model at each voxel independently of the other. You threshold them, and you might have T or Z statistics, or you might have images of parameter estimates. And I think there is the tendency to start sharing these images a little bit more, rather than going from these to just the foci, where obviously you have even less and less control, and it's a loss of information there. So hopefully in the future, people will start sharing these more, and then maybe their analysis as well will have to rely on something that is maybe less affected by problems such as false positives.
Okay, just a quick question, Silvia. So, do you think when you get to that stage of having the more the less processed data, the more raw data, you would still have the importance of your latent variables at the center of the model that you presented?
Yes. So in fact, we have been working on the extension of this model to an approach that does reverse inference, but with data that are both coordinates, as they were in this presentation, and images. So you might have different types of studies in your meta-analysis. Let's say study I gives you foci, and study I prime gives you an image. These unlikely these will ever be raw images, because you can't really share fMRI scans, but at least there is a little bit more of information. Now, as I said, the only thing that changes between these two different types of data is the likelihood. But then the studies themselves are independent. You can have these two components. You change the likelihood, or you accommodate for two different likelihoods, let's say. But then the subsequent levels of the hierarchy are still the same. So you can still use the latent factors later on to link them and to do reverse inference. Now, a question could be, this is not the traditional scalar on image approach. This is in sort of two ways influence, because in one, the two sources of data come in determining the latent factors. One, the foci or the images, and you also have the study types or your outcomes that impact on the learning of the latent factors. So you might say that you are sort of using the response in some sense to learn the model of the predictors. But it's also true that the dimensionality of the data is so that there's probably way more information, right, in an image or in the foci rather than a single study outcome. So hopefully, this shouldn't affect, let's say, the direction of you see the problem.
Yeah.
Can I ask you a question regarding computations?
On computations of the model?
Yeah. So I forget the dimensionality of your images here, but I think it's like roughly 300,000 or so. So if you were to run this, how long does it take?
Yeah. Okay. So the one thing is that so there is nothing in this model that has a dimension of 300,000 times something. So because here we are doing this decomposition through basis functions, and the bases are fixed. So the only thing you have, let's say the biggest dimensionality is the matrix of basis function coefficients, whose dimension is number of studies times the number of bases. Now, the number of bases can be large. Let's say you can have hundreds of bases, but it will never be hundreds of thousands of bases, or at least not the dimensionality of the brain template that you have. So there is nothing really big that you have to invert. There are no big covariance matrices, as opposed to, for example, if you are modeling log mu I through a Gaussian process directly. In that case, you would have a problem, even though there is discrete Fourier transforms that can help you there. But in that case, you would have a problem. This model ran in a few hours in MATLAB, so it's not even code up in some high performance computing. So it doesn't really take much time because you don't have anything that really has the dimension of the voxels here because of the basis functions.
Okay, thank you very much, Silvia. Kirsty, have we any other questions?
Yes, I actually just sent it to you via email.
Okay. I can see one question here.
Yeah, from Han, if you want to go ahead, Silvia.
Question, there are problems if more studies report more foci close together, while a study with a more consecutive threshold only report one local maximum. Okay, so I hope I understand the question. If, let's say, so I think I understand two things, but maybe Han can correct me. So one thing I understand is whether there are studies in my meta-analysis that just come and report one focus, and some studies that report a bunch of them. I guess this is the question. So you could think that so here we are treating all the studies as equal, no matter how many foci they report. So you could say that the study that reports more foci has probably more influence in the analysis in general. There are still not very many foci in general. So yeah, this is a limitation. Or let's say something that the model does not accommodate, because sometimes experiments just eventually report in publication one focus, really the one local maximum, some report more, and so you can say, yes, if there is a study that reports more foci, that probably has a higher influence in your inference as well. Yes, here they're essentially treated as equal, no matter how many foci they report.
Thank you. Kirsty, any other questions?
We do not have any questions at this time.
Okay, so excellent timing, because it's exactly on, well, in my place, 6 o'clock in the evening, but I suspect it's a different time of yours. Fortunately, the Journal Club is recorded, and I think Kirsty has the details of the recording. I'd like to thank everyone who came along for their attention, and it was a very interesting and very informative one. Thank you very much, Silvia, for her presentation, and Mark for his discussant.
Thank you.
Kirsty, do you want to close?
Yep. Thank you guys for joining us today. Like Dr. Todd said, the recording will be available on the IBS website under the Journal Club tab, so you can feel free to listen again and share it. And we appreciate you guys. We will be back in August with our next Journal Club. So thank you again, guys, and have a great week. You may now disconnect from this session.
Thank you.
Thank you.
Bye-bye.